we continue with this problem. We are trying to optimize the function f of x, y, z. I'll remind us it was x squared plus y squared minus z squared. And we're trying to optimize that on the solid unit sphere. So we had checked our critical points because the surface of the sphere gives us a constraint equation or a constraint surface, but the solid sphere includes the interior. So we had to check for critical points on the inside. And then on the boundary, our constraint equation is x squared plus y squared plus z squared equals 1. That becomes the fourth equation in this lovely system of equations. The first three we got by setting the components of the gradient of f equal to lambda times the components of the gradient of g, where g was this function giving us the constraint surface. Okay. So, as always, my overall strategy is try to solve for lambda, set lambda equal to itself to get a relationship between your other variables, and plug into the constraint. But be a pessimist. Think like Eeyore. What could go wrong? So far, we said, oh, if x was 0, I wouldn't be able to solve for lambda in equation 1. So I just recorded, we did case 1 if x is equal to 0, and that actually led to these 4 points on the boundary. Okay, so these cases aren't just things you have to check off. Sometimes they actually lead to possible points. Okay, moving on to equation 2, the next thing that could go wrong is y could be 0. So case 2, y is equal to 0. And you might say, well, we covered that, because wasn't that like subcase 1a or 1b? Only if x was also 0. Okay. So as I'm working through things, if I want to, I can say y is 0 and x isn't 0. Because if x is also 0, that was covered in case 1. Okay. Now, there are certainly some places where y is 0 and x is 0, and those points we already got. But I haven't looked at what if y is 0 and x isn't 0. Okay, so let's look at that. So I'm going to start with equation 2. Equation 2 becomes 0 equals 0, so that is true. Beautiful. Okay. Now, the only other equation that has y's in it is this one, but that would still have 2 other variables. So I think I'll go up to equation 1. Because we've already looked at case 1, I can say any new points will be where x isn't 0. So if x isn't 0, I can divide by it, so I can say lambda is equal to 1. That's helpful. Now let's move to equation 3. So negative 2z has to equal 1 times 2z. That does have a solution. Remember, that means 0 equals 4z, z equals 0. Okay. So we've got, let's see, y is 0 and z is 0. We haven't solved for x yet, but we know it's not 0. And we solved for lambda. We haven't used equation 4. So I use equation 4, and I say, okay, let's see, x squared plus 0 squared plus 0 squared has to equal 1. So I'm plugging in all the information I've gotten so far. So that means x squared equals 1. X is plus or minus 1. Okay. So I've got 2 more points. I've got 1, 0, 0, and negative 1, 0, 0. Excellent. Okay, so I'm just going to record case 2 was y equals 0. And we used the fact that x was not 0 as well, just because otherwise we'd be redundant with case 1. Okay. All right. So now let's take a look at case 3. Could something else go wrong? Well, if I tried to solve for lambda in this equation, something else could go wrong. Z could be 0. So case 3, z equals 0. Now, often as I'm going through my cases, I'll just write that down. But in this case, it's actually going to be helpful to say, I'm going to suppose that x isn't 0 and y also isn't 0. Okay? And that's simply because if x or y is 0, I've already got any points with x or y being 0 covered from cases 1 and 2. Sometimes that extra information isn't necessary, but if I've already considered those possibilities, I can include that here. So let's see what this gives me. Okay, So equation 3 becomes 0 equals 0. So that is true. Equation 1, if x isn't 0, that just tells me that I can divide by the 2x, so lambda is equal to 1. Equation 2, if if y isn't 0, I can divide by it. That tells me lambda is equal to 1. Very good that they're the same. If I got different numbers for lambda, that would be a contradiction and I'd be done. Okay. All right, but that doesn't put any restrictions on x and y. So now I come to equation 4 and I get x squared plus plus y squared plus 0 equals 1. I get x squared plus y squared equals 1. There are infinitely many points that are going to make this true. Okay. If I look at the sphere, okay, what this is saying is if z is 0, so I'm looking at the intersection of this sphere. Now just the surface of the sphere, okay, but the intersection of the sphere with that circle, any of those points is going to satisfy this. Lambda equals 1 makes equations 1 and true pretty clear. Z being 0 makes equation 3 0. That reduces this to I've got to be on the unit circle on the xz plane. So that's giving me infinitely many points. I'm going to describe those points here, as points x, y, 0, but where x squared plus y squared equals 1. So that I've got to actually be on that circle. So we're not talking about the intersection of the solid disk with the xy plane. We're talking about the intersection of the surface of the disk. And that gives me infinitely many points. Points that would be on the unit circle on the xy plane. Okay, that was case 3. Oh my goodness. That led to all infinitely many of these points. Okay. So, like I said, sometimes these cases don't lead to any new points. In this case, we've got a whole bunch of points here. Okay, let's look at case 4. Case 4, x isn't 0, y isn't 0, z isn't 0. Okay. Case 4 is nothing goes wrong. I can divide by all of my variables. Okay. Sometimes this is the only case that students look at because they forget those other cases. They miss these infinitely many points. They also miss a lot of points in terms of partial credit because we spent a lot of time on this problem looking at the problem cases. They really are important. Okay. All right. If nothing goes wrong, then equation 1, I can divide by x, so I get lambda equals 1. Equation 2, I can divide by y, so lambda equals 1. Fantastic, it's consistent. Equation 3, I can divide by z, so lambda equals -1. That's a contradiction. I don't get any points from the nice case. The nice case does not give me any points in this particular problem. Wow. That's kind of exciting. Okay. So, it really was important that we check the problem cases, and that's why I chose this problem, just to make it super, super important. Okay, so let's finish up. This is a list now of my possible places where I could have a max or a min. I need to just plug in to get the w value, what I get when I plug into f. And that was x squared plus y squared minus z squared. So here that's going to be 0 plus 0 minus 1. I'm going to get a -1. 0 plus 0. -1 squared is still +1, so it still becomes 0 minus 1. I get a -1. 0 plus 1 squared minus 0 is +1. Again, I'm going to get a +1. Okay. Basically, if x or y is 1 or -1, when I square them, I'm going to get a 1. So here I'm going to get a 1 plus 0 minus 0 is 1. 1 plus 0 minus 0 is 1. Okay. Now for all of these points, I don't have individual values of x and y to plug in, but I know that x squared plus y squared is equal to 1. So I get 1 minus z is 0, so minus 0, I get 1. So here are my w values. Looks like 1 is the biggest. Okay, so f has a max of 1. It occurs at, now if I wanted to, I could actually just label the points as I had before. I could actually write them out this time. I tend to label them with numbers if I have to write lots of messy fractions. But here I don't, so I'm just going to do it. 0, 1, 0, 0, negative 1, 0, 1, 0, 0, negative 1, 0, 0, and all points of the form x, y, 0, where x squared plus y squared equals 1. That's important. If you just say x, y, 0, you'd be including points like the origin, and that's not a place where we achieve that max. Okay. If you preferred to just call these points A, B, C, D, etc., that would be fine as well. Okay. But this criteria that x squared plus y squared has to equal 1 is a necessary part of describing those points that we got from case 3. Okay. And then I can see the lowest value on here is my negative 1, so f has a min of negative 1, and it occurs at just 2 places, at 0, 0, 1, and 0, 0, negative 1. Good stuff.